Euler's Method, Part 1, an Introduction. Suppose we have a function f of x, but that we don't know what the function rule is. However, there are two things we do know. First, suppose we know the rate of change of f at any point. That is, we know the slope, dy dx at any point. Also suppose that we know a starting point. That is, we know the value somewhere on the graph. Our goal is to approximate values of the function somewhat away from the starting point. So what comes to mind if I know a rate of change, a slope, and a starting point? Well, in my mind at least, I think of a line. Because to write the equation of any line, I need a slope and a point. So let's say we wrote the equation of a line at our starting point. And notice that this line could extend forever in either direction. And we want to use the value of the line to approximate the value of the function at a distance somewhat away from the starting point. Now, at least in this picture, and probably in general, the farther away that we get from the starting point, the worse the approximation the line will be to the function. So instead of using one line, what if we used more than one line? Or that is, what if we use line segments? So at my starting point here, I found the equation of a line, and I found the value of the line some distance away from my starting point. But I know the rate of change of the function at every point. So at this starting point, that is my new one, I could write the equation of another line segment using the slope and this new starting point. And then I could do it again because I have a new starting point and I know the slope at any point. And this way, we can hopefully better approximate the values of the function at a distance somewhat away from the initial starting point. This process of using repeated line segments is called Euler's method. Certainly, if I drew lots of line segments with a very small delta x, and probably using a computer too, I could probably get a very good approximation of the function f of x. Now, there are different ways to set up and figure out Euler's method. That is, we can use tables, we can do certain forms of lines. I will do it in the following method. I personally like point slope form. And then I like to rewrite this a couple times to get to the form that I will use for Euler's method. So the first thing I will do is I will move the y1 over. As such. And then I will change the notation on the right side of the equation. And this is the form I'm going to use to do Euler's method. But to reiterate, I want you to think when you're asked for Euler's method, you're just doing repeated tangent line segments. All you're really doing is writing equations of lines. So let's take a look at this example. Let y equal f of x, where dy dx equals x minus y for all values of x and y. And you have a starting point f of 1 equals negative 1. Let's approximate f of 2 using 2 iterations of Euler's method. Now, when I say 2 iterations, I mean of equal size. So if I start at x equals 1, and we end up at x equals 2, and we have 2 iterations of equal size, then your delta x must be 0.5. So here's how I set up Euler's method. I know a starting point because I'm given that. So I like to write it down over here. I can find the slope at that starting point. My slope being dy dx, which is x minus y. And then I can write the equation of this line at that point and use it to approximate a value of y which is 1/2 away from my starting x value of 1. So the unknown y is my starting y plus my slope times delta x. And I can plug in my values where my starting y is negative 1. My slope is 2. And my delta x is 0.5 or 1/2. Simplifying this, I get y of 1.5 equals 0. Now, y of 1.5 doesn't necessarily equal 0. It's simply an approximation. But this gives me a new starting point. I'm now at the value 1.5 for x and 0 for y. And I can repeat the process. Meaning if I know a starting point and I know that the slope is x minus y, I can find the slope at this new starting point. And then I can approximate my next y value. So I want to approximate y, which is 1/2 away from my new starting point, so y of 2, is my new starting point, if you would, which is y of 1 plus m times delta x. I'll rewrite it out again so we get used to seeing it. And I can plug in my new starting y value, which is 0, plus my slope times delta x, which is 0 plus 1/2 of 3/2, or 3/4, or if you like decimals, 0.75. So using 2 iterations of Euler's method, we see that y of 2, or the function at 2, is approximately 0.75.